Hey everyone, Professor Michael Scanlan here. So I want to tie together some of the things that we've learned over the last few days. So we talked about, you remember, Oersted and Faraday and Lenz. And today we're going to kind of put those together and talk about some practical application, or at least one practical application of this electromagnetic induction concept, where electricity and magnetism are related and affect one another. So I want to show you our setup here. I've got two power supplies behind me, and they are wired to something really awesome right here. Let's take a look. All right, so check it out. Yeah, I know, it's not the best viewpoint of it. Let's turn it around and we'll see what's going on here. So before I turn anything on, all right, let's talk about what we have. I have a shaft that's free to rotate. Okay, it's even got a handle for it for rotation. We're not going to use that today. But this thing is able to rotate. Okay, and as you see, it's connected to this part right here, which has coils on it. Okay, these coils are wired to these metal plates that are wrapped around the shaft, and those metal plates touch these flimsy metal plates. So those flimsy metal plates just maintain contact while this thing is turning. Okay, and they are connected to these posts, these terminals. So that's this shaft part of it. All right, let's look at the front for a minute. Here I can see I've got a metal bar connected to a big coil connected to another metal bar. If we look at it from the top, we see that these bars are isolated. They're insulated. These act as insulators. These bars are isolated. They are insulated from everything else. So the only thing this is connected to is itself. It's this U shape right here, and this is our magnet. This is going to be our magnet, right? So I actually have a setup that does not have a permanent magnet on it, but rather an electromagnet. Okay, so the electromagnet here and here, if we trace it back, is connected to the power supply on the bottom. So all this power supply is going to do is run an electric current through this wire, and as Oersted discovered, that electric current is going to produce a magnetic field, and that's going to magnetize these plates. Okay, so this whole set, or this whole part of the shaft, is going to sit in between basically a magnet. Okay, this is going to be a big horseshoe type magnet when I turn it on. Now, the top power supply is connected to the two posts here, and here, that are connected to these flimsy metal strips, that are connected to the shaft, that are connected to these coils. It's almost like a biology lesson. This bone is this bone, and then this bone and that bone. No bones about it. So what's going to happen is the top power supply is going to run a current through these wires, through the shaft, and then through these coils. So what am I going to have? Let's look at this conceptually. I'm going to have a magnet here, and I'm going to have an electric current here. And that electric current itself is going to have a magnetic field, and they're going to interact. Okay? So I'm going to have an interaction between two magnetic fields. All right? Does that make sense so far? Okay. A magnetic field exerts a force on an electric current because of that interaction. So this magnet is going to exert a force on this coil. And what we'll see is it's going to want to snap it into a stable position. But as it turns through, it has momentum. It can't just stop. Its momentum carries it through. Well, that causes the force to be exerted like that. And so it goes back to its happy place, but its momentum carries it through. And so what we'll see is the magnetic field exerting a force on this coil, on this current, is going to spin it. Watch what happens. So first, I'm going to turn my magnet on, my electromagnet. Okay. And now I'm going to turn the top one on. Now notice nothing happens. Well, there's no current in the top one. I don't know who used these last. Probably a student. All the knobs were up. Students. I absolutely love them. Well, nothing's happening, Professor. Sometimes it just takes a little tap. And what have I made? A motor. If I turn the current or the electricity, it's not enough to keep it going. Down a bit in the top. If I turn it up, it'll spin faster. If I turn it down, it slows down and it just won't be enough to keep it going. There we go. Now, what happens if I turn off the magnet? No force on it. There's still a current in there, but there's no force. If I turn the magnet back on, there it goes. I tell you what, let's turn them both off, and I'm going to switch polarity here. So what was negative will become positive, and what was positive will become negative. Now I want you to tell me, like you can actually hear me, it's like I'm Dora. You can hear me, like I can hear you. Hey, at least it's not boring, right? So I switched the polarities. I want you to tell me, pretend that I can hear you, what's going to happen here. Is it going to turn? Is it going to turn faster, slower, the same? What's it going to do? Let me turn the magnet back on. Electricity. I'll turn this one back on and give it a nudge. Come on. Make it go faster. What is it doing? So we're spinning this way. If I put it back the way I had it, reversing the direction of the current, which is going to in turn reverse the direction of the field produced by the current. So it was spinning like that. Here, come on, work. You might need a little bit more get up and go here. It was spinning like that, and now it's spinning. Come on. Turn it up a little bit. Like this. So reversing the polarity of this current causes the direction to change. So there we go. There's one application of electromagnetic induction. That's the electric motor. And this is a DC motor. I'm using DC electricity. AC is a little bit different, but not horribly so. Anyway, the next video, we're going to look at another practical application of electromagnetic induction. I'll see you then, everyone.